Hi, I'm Philip Bradstock, and this week in Amsterdam at the Wind Power Data and Digital Innovation Forum, I'm going to be giving a talk on maximising operational performance with an operational analytics intelligence platform. However, for those of you unable to attend in person, we're also releasing this video of the talk online as well. So firstly, just to introduce the problem that Bitbloom is solving. If you're not analysing your operational data to deep monitor your assets, you're likely losing revenue in one way or another. And so by analysing that data, you can increase yields due to efficiency issues with performance monitoring. You can detect health issues early to reduce downtime, and that's condition monitoring. You can make sure you're meeting appropriate regulations, and you can help explain your budgets with yield insights. We believe that an open box approach is the way to do that, and with our operational analytics intelligence platform SIFT, we're also already supporting many key players in the industry, helping them to do this. So when I look at this landscape of operational performance analytics, I see that there are many algorithms out there, and then there are many smart people across the industry being able to develop and deliver very advanced algorithms to understand our assets better. However, there's been so many of these with the recent explosion in data science techniques that in many ways we're getting here alarm overload. This is hard to break down and interpret. And with the ever-increasing limited number of analysts we have to monitor each gigawatt of capacity, people simply don't have time to sift through all of these. So my thesis for this talk is that actually it's much easier at an industry level to generate advanced analytics than it is to deliver value from them at scale. So the questions I think we need to answer here is, how do we condense this data so that we can digest it easily? How do we alert well on it? And then once we've done that, how do we communicate the results, bringing in context, really explaining the problem? And then how do we scale these analytics to apply to large portfolios? So I'm going to start with how we condense this data. So in our platform SIFT, we have a very sort of standard template on which we do this, which is sort of designed to be reproducible. So if we sort of start from the top here, sort of we're taking in various sources of data. 10-minute SCADA data is the most widely used in this kind of tool, but also we're using event logs and reanalysis data. And from that, what really we're trying to do first of all is generate classified time series data. So firstly, time series data, typically by turbine, but also that having been classified according to certain flag rules that have been made, or what the event logs are telling us. And then once we have this set of classified, shall we say, raw time series data, we may want to enrich that data in various ways. So this, for example, could be something as simple as a physics-based approach, like density correcting your wind speed measurements, or it could be many more algorithms going to the other end, as some kind of machine learning regression model, for example. But that is where a lot of the sort of intelligence and data science comes in, is creating an enriched set of time series data. But at this point, we're still sort of working primarily at the 10 minutes data. From that enriched 10 minutes data, then we aggregate this data by 3 key steps that I'll go through in a moment, and this produces condensed analyses. And then that set of analyses, then they need to go into a platform that firstly can disseminate this through visualizations, you can alert on it, and then manage the issues and also include possibilities for processing unstructured data that AI now allows, and I'll come on to this later. But this key part, particularly at the bottom here, but condensing those that data into analyses and then disseminating it in this way, this is what we call an operational analytics intelligence platform. In terms of that aggregation step, just to go into that a bit more detail, so this primarily comes by three key steps. So this is first, we need to filter the data in some way. So firstly, we need to filter it for bad data, so to speak, or so-called data cleaning. So looking at valid signal ranges and other things that suggest poor quality data. Rule-based flagging in a multi-dimensional signal space. So this is can be used both to classify invalid data, but also, for example, to feed into then sample classification, like filtering for when the turbine is not derated or down, and this can be considered under normal operation, for example. Secondly, we need to then group the data, also called binning the data, and we would, for example, depending on the analysis, bin this by time period, bin it by turbine, or bin it by certain data signals, for example, by wind speed or direction sectors. And then once you've done that for each group, you simply need to calculate some kind of metric. This metric could be basic statistics like mean and standard deviations, or it could be more bespoke calculations on the data within each one of those groups. So this is a really sort of fairly simple methodology, but this provides a really powerful framework by which we can condense raw information, raw 10-minute data, into something that is more easily processable in the outputs of the platform, delivering that through multi-dimensional KPIs, which is then what feeds into visualizations and alerts. So how do we design good alerts? Well, this in many ways is the key point of why we do that condensing of the data, is that if we just stick to working with 10-minute data or whatever raw frequency it may come in, then the noise level on that tends to be quite high. But as we aggregate that over longer time periods, then these noise levels decrease. So if we think about, if we were to put a simple alert threshold on raw 10-minute data, then you're going to have to put this threshold very high in order to reduce false positives, but also not have too many false negatives. But having it high will actually kind of mean that you are having quite a few false negatives. Whereas if you aggregate in some way over longer time periods, then you can have a much lower alert threshold, which means you have fewer false positives and false negatives. However, that does of course come with the downside of slower time to action, as if you need to wait for a whole month for your alert to be triggered, then you may be missing out on improvements you could have made to the turbines. So where you do this kind of aggregation is really a business question in terms of how quickly you are expecting and need to act on these. So in the context of condition monitoring, that might be more frequently sort of a daily alert level that you need, because you often need to respond quicker, whereas things that result in very small performance efficiency drops, then monthly might be okay, for example. Also, if we look at this in a slightly other way and plot this as a chart of precision, as in can we trust the result or against how sensitive it is, then where we want to be, we want to have both of those things optimally. And if we look at classical statistics on this, then we are bound to a line like this. So it's very difficult to get to the top. Right here, we can have something with very sensitive alerting, but it's likely to throw a lot of false positives, or we can have something that's not so sensitive, but then becomes like naturally very reliable. Given that classical statistics is very good for explaining things, often we Bitbloom would like to put a classical statistic alert threshold much more towards this precision, trustability of the result side of things. But that means sometimes you get some false negatives, i.e. you miss out on some issues, but quite often you would have been able to see them in the data in hindsight. So I call this the land of the benefit of hindsight. However, the point I really want to make here is that the value of combining different analyses to feed into one piece of feed into one issue, multiple pieces of evidence. So what we can do if we bring in more advanced models like machine learning models, often we would design our machine learning place to be designed more to the bottom right of here, so to be really sensitive, because in our opinion, machine learning models often being a black box, even if you make them less sensitive, they can never really fully be trusted. But if you combine the use of machine learning models with more classical statistics, you can actually use them to raise alarms, but then classical statistics to back up that argument with a second piece of evidence. And in many cases, we would go to a second or third or fourth piece of evidence to really make the case for a particular issue. So now that we've alerted on it, that leads us on to how do we communicate the results, providing a holistic explanation of the problem. And I'm just going to make the case here why this is so important. The performance observation that we make has to be communicated to many different stakeholders. And often the role of this data analysis or software or service like ours, we're here as the analyst, and we're providing an observation to the owner. The owner may be feeding that to operators, or they might be feeding it to the site O&M team, and then ultimately they need to go and perform the action on the turbine. So these are several sort of steps of communication that need to happen. But at each step here, we're going to have questions, and all these stakeholders have a right to ask questions and ask, for explanation, do we really need to spend our time looking into this or going and fixing whatever it may be on the turbine? And this slows down action and also costs everyone much more time. So what we really need to enable with these kinds of analyses and platform is strong messaging, keeping communication lines as short as possible, and reducing the need for questions coming back so that fast action can be taken. So that leads me on to issue management. So in SIFT, there is a full issue management part of the software on the front end. And this is a really important part of the tool, because ultimately humans are storytellers. We're not good at simply taking information as a load of data. We need data given in context, and we want to be told a story about what's being observed and what the impact is of that. So in our issue management system, where you can write your observations and impact description in Markdown and link to various charts, really trying to enable users here to tell a story about what has been observed, bringing in appropriate contextual information. We also need to describe the potential impacts of this, and they need to be living entities where multiple stakeholders can come in and make comments and be assigned actions, and for this to develop as a story until ultimately it's closed, either being due to a false positive or due to being resolved or closed in some other way. And developing on this further, we can now really go somewhere with the AI developments that have come out in the last few years. Just want to bring up a couple of features we have newly developed in the SIFT platform here. So firstly, we have an AI search. So this will search through all your issues and analyses in the platform, and more than simply looking for those words. This is a more of a contextual search using embedding models and semantic natural language. Also in documents uploaded to the system, we use large language models to understand and give key insights from those documents. And then finally, and most importantly, with this issue management, we can then automatically bring disparate pieces of information in there. So rather than simply linking those analyses, we can also have it automatically link to various documents in the system that may be relevant for that particular issue, so that you can find them quickly. So this can include many things, such as not limited to maintenance logs and others, for example. So just to then give you a sort of case study of this and to show you sort of how this happens in practice. So I'm going to take what is quite a common type of issue that we monitor in the platform, which is some kind of suspected performance or power performance degradation. So one of our analyses that we typically have is called power curve efficiency in partial load, and we can see here for this particular turbine that it's quite a noisy signal, but over the last few months, I think these are our weekly points, we've really seen a drop in that performance, power performance efficiency, but given the noise, we probably want some other piece of information. So from this, we create our initial issue saying there's performance degradation, but then we bring in some other pieces of information. So we have a wind speed from neighbours algorithm to check whether there have been nacelle wind speed measurement changes, because more often than not, an observed change in the power curve is actually due to nacelle anemometer calibrations rather than actual change in performance of the turbine. We can also bring in turbine maintenance logs then to see whether anything has been done on the turbine recently, whether it's related to the nacelle or anything else in the turbine that may affect performance. We can look at the production trends of this turbine versus others. So now ignoring wind speed, but just looking at power relative to other turbines. And then we can also do side-by-side tests where we compare both wind speed distributions and power distributions with a neighbouring turbine. And so bringing in all this supporting information, we can make an issue with a strong evidence base that brings in a lot of context, that tells a nice story that reads well, and that other stakeholders can then come in, view that, can be assigned actions, and can also write comments on and help resolve this issue quickly through efficient software. So now, how do we scale these analytics to apply on entire portfolios? Well, this really comes back to what I was mentioning at the start about this template that we use. As I said before, it's not fantastically complicated, but pretty much all that we do around data analysis of time series data falls into this pattern. So once we've got that pattern, we can then use this as a template and duplicate it across the portfolio. So copy and repeat using parameterization. So we map shared SCADA signals using aliases. So what this means is there is a SCADA signal on each turbine type on each site. That means your 10-minute wind speed average, for example. It's generally called something different, but we have a system of mapping those using aliases. Of course, there are some cases that are slightly more complex in terms of the components and the nacelle, for example, not being exactly the same across different sites. But for the large majority of signals, we do actually have like for likes there that we need to have a consistent mapping for, so that we can template analyses. And then we have various turbine parameters. So these are things like rated powers, rated generator speeds, all things about the turbines or the site, which then means we can set up rule-based flagging, in part relative to these parameters, but also the flagging. This is where often it does need to be on a case-by-case basis, because, and I think generally speaking, this is one of the most important parts of performance analysis, not actually the algorithms you're doing sort of downstream, but the how you classify the data and how you filter the data is very important. And so this is actually a part where there is more human effort going in to make sure that you do that really well. But ultimately, once you have rule-based flags, rules can be repeated and scaled as well. Mapping of event codes to subclassifications is often the same for particular turbine manufacturers, and that can be repeated. And as I say, flags can sometimes be reused between sites of the shared turbine types, but not always. You have to check. Then finally, analysis definitions and visualizations are templated on all of that, so that they can be reproduced for their individual signals and classifications. So to conclude, I have presented what we call an operational analytics intelligence platform. That is one that can condense large amounts of data, has sensitive but precise alerting, a holistic discussion of issues, and can be scaled over full portfolios. And so we're putting this into practice of, at the moment, around 5 gigawatts of assets, very geographically spread across the globe for a very sort of disparate set of turbine types, and including solar PV as well. And that allows us to use about 1 full-time employee analyst for every 2 gigawatt that we're monitoring, with full monitoring services. And with all this information in there, this is also ready for the AI revolution. So thank you very much for listening to this talk. If you want to find us at any events you may be going to, we'll be in the Wind Europe annual event in Copenhagen, we'll be in Intersolar in Munich, All Energy in Glasgow, and then at the Wind Europe Technology Workshop in Istanbul in June. If you want to book a call with me, you can just scan this QR code here to go to our meeting booking software. So thank you very much for listening, and hope to see you all soon.